By now, we're assuming you've seen the Reddit threads, TikToks, and tweets, and news articles, and we want to give you a timeline of what's transpired and some transparency into our decision making.
We've been doing this channel for a month now, and our numbers don't look that good. We've only gained 100 subscribers in this time. When you look at a channel like Mr. Beast, he's gained over 1 million.
And thus, we have begun an intensive process of engaging with YouTube, the SI coordinators, Dr. Duma, and more to make a change to do better.
What's up, guys? It's the Biochem creators coming back to you again with nitrogen metabolism, and guess what? We're at 100 subs. That's right. Yeah, give yourself a pat on the back. We reached it. You know what that means? We got the face reveal coming in the next video or sometime soon, because you don't know what our faces look like. That's right. You have no clue. But make sure. Look at this graph. Look at this graph. I see that a lot of you aren't subscribed, and a lot of y'all are watching our videos, so make sure you smash that subscribe button right now. I don't see you hitting that button, so please do that. But let's get into the overview of our video today. So today we're going to be talking about three main things. So first, amino acid biosynthesis. How are we going to create a lot of the amino acids that we are familiar with? And then we're going to talk about the steps of purine pyrimidine nucleotide biosynthesis, which will be very helpful when we talk about that in Unit 4, when those are important for DNA, RNA, etc. And finally, we're going to talk about Dr. Zeile style questions, because he kind of formats his questions in a very unique way, and that's what we're going to cover today. So without further ado, I'm going to hand it off to amino acid biosynthesis.
Hey guys, so our amino acids are categorized into 3 different categories. We have nutritionally essential amino acids, conditionally essential amino acids, and then non-essential amino acids. So for our nutritionally essential amino acids, these are ones we need in our diet, right? We can't synthesize them, so we need to consume them. For our conditionally essential amino acids, they are conditionally essential. So under certain conditions, we're going to need more of these amino acids in our diet. These are arginine, tyrosine, and cysteine. You can memorize them with this acronym CRY. The remaining amino acids are non-essentials. We have ways to synthesize them. In this section of this video, we're not really going to talk about all of these amino acid biosynthesis pathways. I'm just going to focus on 2 or 3 or 4 that I think are essential to know for the exam. Starting with arginine, the major pathway producing arginine is the urea cycle. Glutamate undergoes reduction to form glutamate semialdehyde. That glutamate semialdehyde undergoes transamination to form ornithine. Ornithine then participates in that urea cycle, which is that last video that we did. Ornithine then eventually forms arginine. So it's important to understand that glutamate is a precursor for arginine. Arginine can then form nitric oxide and creatine. Creatine can then get phosphorylated and serve as a ATP buffer within our muscle cells as creatine P. Once that creatine P is used up, it forms creatinine. Creatinine is the breakdown product of creatine P. It is produced at a fairly constant uncatalyzed rate, and its yield depends on muscle mass. It is typically higher in males than it is in females, and clearance rate tells us how well the kidney is working. So moving on to alanine. Alanine is formed solely by transamination from pyruvate. The glucose-alanine cycle sort of discusses that process. Starting off in the muscle, we have glucose. That glucose is used during glycolysis to form pyruvate. If our muscle is active, right, we're doing a lot of glycolysis and we're not moving that pyruvate into our mitochondria to then undergo that citric acid cycle, which we'll talk about in Unit 3 with Zeile. Instead, that pyruvate is transaminated to alanine, remembering that the KEQ for transamination is 1. So if we build up pyruvate, we can easily move to make that alanine. Alanine can then get transported via the blood to the liver. In the liver, alanine will then get transaminated back to pyruvate, and that pyruvate will then get incorporated into glucose, and that glucose can go back to the muscles or the brain or any vital organs that need it. With proline, I am confident that there will be a proline biosynthesis question on the exam. Right, so it's really important to understand the process as well as the enzymes that are involved. You don't need to know their names particularly, right? Just the fact that they're a reductase, a cyclase, and then another reductase. So we're going to start off with glutamate. Glutamate will be reduced to form that glutamate semialdehyde. Remember that that's a precursor for arginine, right? It can undergo transamination to form that L-ornithine, which again participates in the urea cycle and moves through to form arginine. Or it can be acted upon by a cyclase. That cyclase will form this sort of cyclic structure, which will undergo another reduction to form proline. This is really important to understand because it's sort of a convergence point in this amino acid biosynthesis section, right? Proline is not only important for arginine, it's also important for hydroxyproline. So as I mentioned, proline is important for hydroxyproline. Hydroxyproline is essential for the stability of collagen because it forms key hydrogen bonds within that triple helix that forms collagen. Hydroxyproline is synthesized from proline by prolyl hydroxylase. This is an iron-dependent reaction. Specifically, we're using Fe2, right? And you can see the reaction right here. That Fe2 can easily be oxidized to Fe3. That's a problem because it deactivates our prolyl hydroxylase, preventing it from forming this hydroxyproline, which is essential for collagen. To prevent that, to reverse that oxidation to Fe3, we have vitamin C or ascorbic acid. Ascorbic acid will restore prolyl hydroxylase, allowing us to form hydroxyproline and allowing us to make collagen. So now we have tyrosine. Tyrosine is synthesized from phenylalanine by phenylalanine hydroxylase. This is a two-step catalytic process, but you don't really need to be aware of the specifics of this two-step catalytic process. Just be aware that we're making tyrosine from phenylalanine. Phenylalanine hydroxylase deficiency results in phenylketonuria, right, which is the buildup of phenylalanine in the blood and in urine. This is a treatable disorder. The most important thing to be aware of this disorder for the purposes of this class is that we're going to have a buildup of phenylalanine, but we're going to have very little or low tyrosine. That's going to be important because tyrosine serves as the base for T3 and T4 biosynthesis. So this is T3 and T4 biosynthesis sort of summarized. I'm not really going to go over it just because it's sort of broken down. So, take a look at this slide. Make sure to really understand, the process here because you might get tested on what comes first, what comes second. So just take your time, try and memorize this stuff. Again, phenylalanine hydroxylase deficiency results in phenylketonuria. And when we have a lot of phenylalanine and very little tyrosine, we will struggle to make this T3 and T4. So that's sort of like a application style question that you might see on the exam. And now on to pyrimidine and purine nucleotide biosynthesis with Fran.
Hey guys, it's Fran, like Victor said. I'm here to talk to you guys a little bit more about the pyrimidine and purine nucleotide synthesis. So a couple of general things that kind of have to do with both pathways. Again, first obvious note here, definitely know your pyrimidines and purines. Because those are definitely become helpful, especially like Victor kind of touched on in Unit 4, where especially it comes in DNA and RNA. And so your pyrimidines are going to be UMP, CMP, and then deoxy-TMP. Remember, TMP only exists in the deoxy state because it's in DNA, not in RNA. And then your purines are going to consist of your IMP, AMP, and GMP. And so UMP and IMP are the respective pyrimidine and purine precursors. Again, we'll get into that in a second, but the pathway itself. Well, the key thing for these, I know that it does seem very dense and there's a lot of structures being thrown at you and a lot of steps involved. What you really want to understand for all the steps is just really understanding the chemical logic, kind of throw that term at you a lot. You really want to be really comfortable with the reaction arrow itself because typically how they ask questions on the exam is you're going to be given the actual images of some reactant or product of one of the steps and it's up to you to remember what exactly is involved in the reaction to cause it to go from A to B. So definitely keep that in mind. Another small note here lastly, the activated sugar intermediate of phosphoribosyl pyrophosphate, that's just going to be how the ribose sugar is added on to the nucleotide. That just again, wrote that there, nothing too crazy there. So without further ado, we'll get into pyrimidine biosynthesis. And so right here, I have all the steps laid out. I'm not going to really talk about these because again, these are pretty much straight from your slide, but I am going to reiterate again. Definitely just keep in mind what's on that reaction arrow, so essentially what's highlighted, that's what's important, understanding what causes the change and what units are involved in the change. But again, don't worry about the structures, you should be given images typically on the exam for stuff like that if they do want a quiz on it. And so we'll get started, we're going to do a quick little question on pyrimidine biosynthesis. So just like this, typically usually get some sort of image, excuse my wonderful artistic skills, but you'll get much better images on the exam. And so the question here says, this step in pyrimidine nucleotide biosynthesis is an example of a oxidation or reduction reaction and uses the cofactor blank. And so again, if you look at the reaction arrow, looking at what changes between the pictures, we see that from A to B, we're adding a double bond onto our molecule. And so that's going to be an example of an oxidation reaction. And typically the main cofactors involved in oxidation reaction is going to be NAD+. That's the main kind of thing there. And so looking there, beautiful. And so right here, we're going to add some couple more questions for you to pause the video as they come up and answer them yourself before the answer comes up. And then yeah, moving on, we're going to get on to purine nucleotide synthesis. Purine biosynthesis, again, very similar thing, a lot more steps involved here because there's a 2-ring structure for purines as opposed to the 1-ring structure in pyrimidines. So again, I'm not really going to go into depth with a lot of the steps because it's kind of just knowing the steps themselves and really understanding what's changing from A to B. And like looking at the pictures again when you're given them or you see them on your lecture slide, just looking for the change that happens from A to B really gives you a good indication of what exactly is being added or taken or something off of the molecule. So again, we're going to go over some question styles. I'm going to do one really quickly here. So again, image here, we go from A to B there. We see the one really unique change here is that we're adding a succinate molecule onto our overall building block here. And so typically when we see succinate, the question's asking us which amino acid is used as a substrate in this step, purine nucleotide biosynthesis. Typically succinate is going to always hint at aspartate, that amino acid being involved in some sort of reaction. So right there, as you can see, again, one of the other amino acids involved in purine nucleotide synthesis is actually glycine. I believe that's going to be in step 1 or 2. Again, double check your lecture slides again. I'm going to reiterate one last time. For these style of questions, definitely just keep in mind again the reaction arrow because typically the pictures will be given to you. Don't really stress about the structures there. You already have enough structures to know about for this exam in general. And so just like purine nucleotide synthesis, here are a couple more questions going to pop up on the screen. Feel free to pause them as you see them, answer them, and then let the video play and you'll see the answers. Last little thing here, this side is probably important for like the regulation pathway for all your purine nucleotide synthesis. Thankfully, it's kind of self-intuitive in that you see how INP is a precursor, INP will lead to the production of the AMP and GMP, and those are kind of self-reasonable there. So like example here, for the first part of regulation here, AMP inhibits AMP synthetase, which directs INP to GMP. That's just a really fancy way of saying if we have really high AMP levels, we're not going to make more of it, we're going to drive the formation of GMP. And then likewise for step 2, it says the exact opposite. If we have really high GMP, it's just going to direct the pathway to the INP path, or the AMP pathway, sorry. So just keep in mind of that. Just think about it from like a chemical logic sense. Love that term. Think of it just rationally, use your common sense. If we have a lot of one thing, but it makes sense for us to keep making more of it, we go another route in the pathway. So that's all I have for pyrimidine and purine nucleotide synthesis. Nothing really crazy there. I didn't go over a lot of the steps because again, they're right from your lecture slides. I know you guys can look at those. And yeah, again, read it one last time. Focus on the reaction arrow, not the pictures themselves. And so now, to pass on to Michael for some Zeile style questions.
Alright y'all, it's me back again with, you guessed it, the Dr. Zeile question overview. So you might be asking, who's Dr. Zeile? Well, I hope you would know. You should be going to lectures. But if not, he's going to be the other professor teaching in the second unit. And you'll be teaching, like a couple of these lectures at the end that's not going to be related to nitrogen metabolism. So he has this specific style of writing that you kind of have to get used to when he writes his test questions. And it's very like big blocks of text that you have to kind of parse through and kind of understand what he's trying to ask. So we have developed as SIs, especially a lot of credit to one of the old SIs, his name is Ethan Kramer. He developed like these 2 ways of kind of distinguishing Dr. Zeile's questions and then kind of parsing through that and just working through that. So most of his questions actually boil down to a single sentence at the end, but then you kind of just have to see what the rest of the paragraph is asking for and what you need to know. And also, not all of Dr. Zeile's questions are going to be like this, only a couple. Like some will just straight up just be recall, like what you're used to, like what you saw in Unit 1. But other than that, there are going to be 2 main types of Zeile style questions that we'll call them now. So the first is pseudo-discrete, which is basically just testing recall, but it's still in that giant chunk of paragraph. The second is inference, and that tests understanding. So let's take a look at what that would look like. So there's 2 main steps that you want to do. First is to look at the last sentence first. So usually the last sentence is literally going to be the question. So it would be like, blah, 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 here's a bunch of background, and then what does blank mean doing this. And then you can see like what exactly Dr. Zeile is trying to ask. The second thing is to actually read the entire paragraph. Yes, it's going to be long and annoying, but especially for those inference questions, you need to read it just because it will give context that you're able to derive like the answer and be like, oh, that makes sense why it would be this choice rather than this choice. And it also provides more information to confirm your answer for pseudo-discrete even if you know it off the bat. So with that being said, let's take a look at some examples. And spoilers ahead, we are going to use examples from Dr. Zeile's practice document that he should post in the modules. But yeah, just saying that. So if you don't want to read and watch the video, you can skip. But it's a really helpful tool, so how to parse through these questions. So I would recommend you do so. Alright, so let's practice pseudo-discrete. So let's read this question. I'll just read it out really quick. After ingesting water, food contaminated with the bacterium Vibrio cholera, the toxin secreted by the bacterium attaches to the epithelial cells lining the intestines through a binding interaction with gangliosides of the plasma membrane of those cells. Which of the following is a characteristic of the gangliosides? So, what type of question is this? It's pseudo-discrete. So, what we're looking for is first to look at the last sentence. So, highlight whatever, underline whatever you can do to kind of make that stand out, and that's what you know is like, oh, this is literally just asking what is the characteristic of a ganglioside. Like, you don't necessarily need the rest of the paragraph. You can use it as context, but if you know the straight up answer from this recall question, then you can just answer it. So you can be like, okay, what gangliosides? That kind of sounds familiar, and if it does, that's good, because that's going to be related to those sphingolipids that he talks about in one of the lectures. I don't know if it'll line up exactly with how ours do, but yeah, ganglioside is an example of a sphingolipid. So it's going to be answer choice C, a fatty acid attached to a sphingoside by an amide bond, right? Because sphingolipids have that unique amide bond in their structure. Okay, so that's pseudo-discrete. Alright, so let's practice with a inference question. So this is a super long text, so I'm not going to read it, but if y'all want to just pause the video for a second and just take some time to read it. Alright, so let's go through our steps again. So remember, always with these Zeile style questions, we want to highlight what is the last sentence and then see what it's asking. So let's do that. So when we highlight it, we see it's asking what would be the consequences to the intestinal cell. Alright, you don't know what that's asking. Like, that is not pseudo-discrete because you cannot come up with the answer immediately. You know, compared to the pseudo-discrete question, it was like, oh, what type of, what is this ganglioside thing? And it's like, oh, it's that. But here, you have to know what the question, like the context of the question, because like, I don't know what the intestinal cell is asking for. Like, it's very correlated to the context of the paragraph. So that means we have to read through the paragraph. So let's read through the paragraph. One thing that helps a lot is to kind of break down the paragraph into chunks, especially into details that you recognize as like keywords that you've seen in the lecture, because a lot of times these paragraphs are going to have extraneous information that you don't need to know. So for example, the first sentence, it says, one of the clinical cases presented involved eating food or drinking water contained with the bacterium Vibrio cholera. Do you need to know what Vibrio cholera is? No, you don't. But it's just there because it ties in like real world application, and you'll see that in Dr. Zeile's clinical case things, but you don't need to know that. But if you look at further details, you'll see things like actually line up with what you've learned in lecture. So for example, in the second sentence, it says it modifies the alpha subunit of a G protein coupled receptor in the family of the beta adrenergic receptors. So that's something that you recognize, like, oh, GPCR, I do remember learning about that for the signal transduction pathways. And yeah, and that's where you start applying the knowledge that you've learned. So the specific context of this question, we're going to look in the third sentence when it says the alpha subunit is modified. Remember, the alpha subunit is going to be that part of the GPCR pathway that's going to be able to trigger the effector enzyme, like adenylyl cyclase, and then have those second messengers activate. But we're looking at it that it's actually a modified alpha subunit, and it says in the fourth sentence, it has an intrinsic GTPase activity, and it is lost its intrinsic GPase activity, and that it just keeps on, it's still able to do the exchange that activates the enzyme. So now we combine all these facts together, and you have to think, okay, so it's a GPCR, and our alpha subunit is weird, and in the way that it turns on and it can't turn off. So when we look at it, that means all these above details are leading to this fact. All of them are involved with the regulation of activation, and that we have lost the control for the regulation. So if we've lost the control for the regulation of activation, that means there's less regulation in general, meaning that this process is going to always constantly be on. So for these inference questions, like you have to look at what the details are implying. So here it's like, oh, it's implying that regulation is turned off. And it's always going to be a concept that we learn about. It's not going to be some like random thing that Dr. Zeile has not taught. Okay? So for this question, the answer choice will be A, unregulated activation of down low cyclase in increased levels of CAMP, because our alpha subunit of the G-coupled protein receptor will not turn off. It's always going to be on. It's going to be continuous, and then keep on sending that signal for the second messenger. Okay, so how do I study for more Zeile questions? So first, I talked about it in that little spoiler part, but there should be in your modules under Unit 2, there will be a practice exam for Dr. Zeile. He has questions, both the easy ones, like that are not Zeile styled, and then also Zeile styled. And then there's also some other ways that I would suggest. First is like asking why. Why are all the other answer choices wrong, right? So you can kind of understand what he's asking. I think a fun one is to try to make your own Zeile style questions. It's really easy. Like you can go to Wikipedia, pull some random fact that kind of correlates, and then slap on some actual things that you've learned, and then ask a question. That's kind of how you could do it. Or you can use the clinical cases he uses. But yeah. And then another way is to try to explain the answer to people that are like a 7-year-old, so then you can really grasp it. And there's other ways, like make sure you're not just memorizing, you're understanding, etc., etc. Okay? But yeah, so that's the Zeile style question, and I hope that helps y'all. But we will now send y'all to the outro.
So that's all we have for you guys today. Hopefully you guys found that helpful in some way. As always, feel free to check out the resources we put at the end of the video. And we'll see you guys next week for our exam review. Peace.
I don't know why I clapped. I felt like it was.
And then.
Yeah.